First question is how to draw pressure, volume and temperature entropy diagram for dual combustion cycle, which is thermodynamic air cycle. Second question is solve one problem by using the different formulas for the dual combustion cycle. Let us understand how to draw pressure, volume and temperature entropy diagram for dual combustion cycle. As dual combustion cycle is thermodynamic air cycle, that is, air is enclosed in this piston cylinder arrangement. If we observe this diagram, here is hot body, insulated cap and cold body is brought in contact with the bottom of the cylinder. Now we will consider the initial condition of air. M kilogram of air is enclosed in this piston cylinder arrangement, which is at pressure P1 and volume V1. So we will select here one particular point for pressure P1 and volume V1, and it is at temperature T1. So here will be the point 1, which is at temperature T1. In dual combustion cycle, two processes are taking place at constant volume. Two processes are reversible adiabatic or isentropic processes, and one process is taking place at constant pressure. Now when we observe these processes and to draw this diagram, we have to must note down what is the relation as per these processes are taking place in between this pressure, volume, temperature and entropy. And that relation is important, that you have to note down in your notebook. So we will move for the first process. So first process is constant pressure heating. So here heating process is taking place, but it is at constant pressure. If we observe this diagram, hot body is brought in contact with the bottom of the cylinder and the heat is supplied. So the heating process is taking place. Now during the process 1 to 2, we have to show heating. Now at point 2, heat supplied is cut off. So this point 2 is known as the cut off point. Now I will write here the relation. So what is happening during the heating process? So we know that during heating process, its temperature is getting increased. So I will show here increase in temperature. During heating process, entropy is also getting increased. So entropy is also getting increased. So we know that here as temperature is increased, that means pressure is also getting increased. So I will show here pressure is also getting increased, and as the pressure is getting increased, that means volume is getting decreased. So this is the relation, that this is the common relation every time we will apply for the processes. But for this process, pressure remains constant. So this pressure, instead of increasing, it remains constant. So we have to show, so when pressure is constant but the temperature is increasing, then here instead of volume decreasing, this volume is getting increasing. So this is the relation that we have to note down when this condition is applied. Now we will show this process. So because of the P constant, we have to show increase in volume. Here will be the volume V2. Then temperature is increased and entropy is also getting increased. Then what is the amount of heat that is getting absorbed? That is mCp T2 minus T1. Now Cp, that is the specific heat at constant pressure. So why we have to take that? Because this process is taking place at constant pressure. Now we will move for the next, reversible adiabatic or isentropic expansion. So for this process, insulated cap is brought in contact with the bottom of the cylinder and no heat is absorbed and no heat is rejected during this process. Now again we will apply the same relation. So here entropy remains constant. So we have to show here this E that will remain constant. And now what is the effect on other parameters? That is pressure, volume and temperature. Here the expansion process is taking place. So when the expansion process is taking place, so we know that its pressure is getting decreased. So we have to show here the decrease in pressure. So what is the relation in between pressure and temperature? So as pressure decreases, temperature also decreases. And when pressure is getting decreased, volume is getting increased. So we have to show increase in volume. So this is the relation. So we have to show entropy constant. So why entropy constant? Because no heat is absorbed and no heat is rejected. So we have to show E constant. Now we will show this relation. So P decreased, V increased. So we have to select point 3 in such a way that P should decrease and V should increase. So here is the V3 and this is the relation. Then from 2 to 3 we have to show constant entropy but temperature decrease. So again we will show here. Here will be point 3, that is temperature T3. Now we will move for the next process. So we will show arrow also here. Next process is constant volume cooling. So here constant volume, that means we have to show volume constant. And for the cooling process, when cooling process is taking place, when this cold body is brought in contact with the bottom of the cylinder, then cooling process is taking place. Now we will find out the effect. So here volume is constant. Now what is the effect of cooling on other parameter, pressure, temperature and entropy? So it is easy to understand. Temperature is getting decreased. So because of cooling, temperature is decreased. So as temperature decrease, pressure is also getting decreased. So here pressure is also getting decreased. And during cooling process we know that as heating, entropy increased, during cooling entropy decreased. So for the entropy it matters for the heating and cooling process. So for the entropy it is decreasing because of cooling. So now we have to plot this relation. So pressure decrease and volume constant. So here will be the point 4, P4. V3 is equal to V4. Then we have to show decrease in entropy and decrease in temperature. So point 4 should be below than this. So we will show here the point 4 and I will show this. So if I plot here the point 4, then here will be the temperature T4 and its entropy is getting decreased. So I will show here this S4. During cooling process, heat is getting rejected. So what is that amount of heat rejected? That is Q34 is equal to mCV T3 minus T4. Now here specific heat at constant volume, because process 3 to 4 is taking place at constant volume. So we will make here arrow. Now we will move for the next process. So process 4 to 5. Here reversible adiabatic or isentropic compression process. Insulated cap is brought in contact with the bottom of the cylinder and the compression process is taking place. Now we will observe what is the effect of compression on pressure, volume, temperature, because here entropy remains constant because no heat is added or rejected during this process. So we will show here the constant entropy, that is I will show E constant. Now what is the effect of pressure, volume and temperature? So what is happening during compression? So during compression we know its a pressure is getting increased. So as pressure is getting increased, temperature is also getting increased. So here is increase in pressure and temperature. So as pressure is getting increased and volume is getting decreased. So this is the relation that you have to note down. Now we will show this all the processes. So we have to show increase in pressure. Now we have to select point 5. but we have to take one care, that is we have to increase the pressure in such a way that P5 should be greater than P3. So here is the pressure P3. Now we have to take this slightly greater, that is here will be the point P5, and now I will join this process, that is pressure is getting increased and volume is decreased. So we have to show decrease in volume and increase in pressure. So here we have to take the P5 is greater than P3. Now we have to show constant entropy but increase in temperature. So again here is T3 is there. So here we have to take care of one point, that is T5 should be less than T3. So here we have to show P5 should be greater than P3 but T5 should be less than T3. So this is the relation that we have to consider, and because of constant entropy we have to show here this straight vertical line. So we will show this vertical line. So here will be the point 5. Now we will move for the next process, that is process 5 to 1. So during this process constant volume heating. So again hot body is brought in contact with the bottom of the cylinder and the volume remains constant. Now this is the important point. So what is the effect on other parameters when heating process is taking place? Now here volume will remain constant. So during heating we know that its entropy is getting increased, so we have to show increase in entropy. So during heating temperature is also getting increased, so we have to show increase in temperature, and as temperature increases we have to show increase in pressure also. So we have to show all these processes. Now if we move for this PV diagram, volume constant, that is we will take here V5 is equal to V1. So V5, that is at point 5, V5 is equal to V1. Volume constant but pressure increases, so we will join these 2 points. We will show arrow also. Then entropy increases and temperature also increases. So here increase in entropy because S4 here, then S4 is equal to S5 and here is S1. So S1 is greater than S4. So entropy increases, temperature also increases because T1 is greater than T5. So we will join these points. Let us understand the different formulas related to dual combustion cycle. First one is work done. So we know that work done is equal to heat absorbed minus heat rejected. For dual combustion cycle, heat is getting absorbed for two different processes, and these processes are process 5 to 1 which is taking place at constant volume and process 1 to 2 which is taking place at constant pressure. So during these two processes heating is taking place and that's why heat is getting absorbed. So how to write this formula? So mCp T2 minus T1, because 1 to 2 process is taking place at constant pressure. So mCp T2 minus T1 plus we have to add this heating process, that is which is taking place at constant volume, that is V1 is equal to V5, mCv T1 minus T5. So this is the formula, minus heat rejected. So heat is getting rejected during the process 3 to 4 which is taking place at constant volume. So during this process cooling process is taking place, so we will write the formula minus mCv T3 minus T4. Now we will move for the efficiency. So efficiency is equal to work done by heat absorbed. So for work done we will write this whole bracket, and for denominator, that is heat absorbed, we will write this first bracket, that is this only heat absorbed. So when we simplify this we will get the formula 1 minus T3 minus T4 divided by gamma T2 minus T1 plus T1 minus T5. This gamma is the ratio of Cp by Cv. That is, it is the ratio of specific heat at constant pressure to the specific heat at constant volume. We will understand the relation in between different parameters, pressure, volume, temperature and entropy during the different processes. So first one is compression ratio. So when the compression process is taking place, so if we observe during the process 4 to 5, this compression process is taking place. That is, we have to take the relation for the volume at point 4 and this volume at point 5. So we will take V4 by V5, which is equal to compression ratio. So this V5 is equal to V1 and this V4 is equal to V3. So we can write here V3 by V1 and we will write the notation for compression ratio, that is R. Next one is the cut-off ratio. So we know that at point 2 heat supplied is cut off and this point 2 is known as the cut-off point. So we will take the volume ratio for the process that is at point 2 and 1. So cut-off ratio is V2 by V1. Now if we observe V1 is equal to V5, so we can also write V2 by V5, and for cut-off ratio we will write the notation, that is rho. Then pressure ratio. So this pressure ratio, that is, we have to take during the process 5 to 1 because this process is taking place at constant volume. So this pressure ratio is P1 by P5 and here notation is alpha. Now we will move for the next process at constant volume heating. So when the heating process is taking place at constant volume, that is during the process 5 to 1. So at constant volume heating, what is the relation in between pressure and temperature? Because here V remains constant. So we have to keep in mind one relation, PV is equal to T. So here V remains constant. So this V is constant. So we can say that P by T is equal to constant. Or we can also say here P1 is equal to T1 and P5 is equal to T5. So we can plot any relation. So if we take the ratio on both sides, then here P1 by P5 is equal to T1 by T5. Or we can write P5 by P1 is equal to T5 by T1. So we have to write this. Now in the same way, at constant pressure, what is the relation in between V and T? So at the constant pressure, if we observe, so here is the pressure during the process 1 to 2, pressure remains constant. So what is the relation in between volume and temperature? So same relation is there, PV is equal to T, but here P remains constant. So we can write here during the process 1 to 2. So we have to consider point 1 and point 2. So V1 is equal to T1 and V2 is equal to T2. So we can take the ratio, that is V1 by V2 is equal to T1 by T2. So here is the relation. Then we will move for the isentropic processes. So isentropic expansion process. So when expansion process is taking place during the process 2 to 3, here is the isentropic expansion process. So what is the relation in between temperature and volume? So temperature and volume relation, that is T3 by T2 is equal to V2 by V3 raised to gamma minus 1. Here gamma is the isentropic index, which is equal to Cp by Cv. Then isentropic compression. So here 4 to 5 is the isentropic compression. So T5 by T4 is equal to V4 by V5 raised to gamma minus 1. So these are the important formulas that we have to use while solving the problems. We will solve one problem. I will read what is the given question. Engine working on dual combustion cycle has a pressure of 1 bar and 50 degrees Celsius before compression. The air is then compressed isentropically to 1 by 15th of its original volume. The maximum pressure is twice the pressure at the end of isentropic compression. If the cutoff ratio is 2, determine the temperature at the end of each process and the ideal efficiency of the cycle. Take gamma is equal to 1.4. Let us understand what is the given data. It is given that before compression pressure is 1 bar and temperature is 50 degrees Celsius. Now we will observe this diagram. Where is the compression process? So process 4 to 5 is the isentropic compression process. So before compression, that means we can say that at point 4 pressure is given and temperature is given. So we will say here P4 is equal to 1 bar and T4 is equal to 50 degrees Celsius, and we have to convert it into Kelvin, that is 323 Kelvin. Then isentropic compression is to 1/5 of its original volume. So this compression process is taking place in such a way that its volume will be equal to 1/5 of its original volume. So if we observe, after compression volume is equal to V5. So this V5 is equal to 1/15th, that is 1/15th of original volume. So original volume, that is before compression, that is at point 4. So V5 is equal to 1/15th of V4. So we have to take this relation. So instead of V5 we can also take V1, and instead of V4 we can also take V3. So from this diagram only we have to write this. Then maximum pressure is equal to 2 times pressure at the end of compression. Now if we observe this diagram, here is the maximum pressure, that is pressure at point 1 and pressure at point 2. So we will write here P1 is equal to P2, which is equal to 2 multiplied by pressure at the end of compression. So here is the compression process 4 to 5, that is 2 multiplied by P5. So this is the relation that we have to use. Then cut-off ratio is equal to 2. So what is this cut-off ratio? If we observe, at point 2 heat supplied is cut off. So we will take the volume during the process 1 to 2, that is V2 by V1. So we will take here V2 by V1 is equal to 2. Now V1 is equal to V5. So we can also take here V2 by V5 is equal to 2. And gamma is equal to 1.4 is given, and we have to find out the different temperatures at the end of each processes, that is at the end of this compression process, at the end of this heat addition process, then at the end of this expansion process, and at the end of this cooling process. And we have to also find out the efficiency. First we will find out the temperature at the end of isentropic compression. So here is the isentropic compression process 4 to 5, and therefore we will find out temperature T5. Now this is the isentropic process. So what is the relation in between temperature and volume? That is T5 by T4 is equal to V4 by V5 raised to gamma minus 1. Now we have given data V5 is equal to 1/15th V4. Now here V4 by V5, that is V5 we will transfer to the right hand side and this 15 to the left hand side. So T5 is equal to T4 into 15 raised to 1.4 minus 1. So what is the answer? T4 is 323, that is given in the data, and 15 raised to 1.4 minus 1, that is 2.954, which is equal to 954 Kelvin, and which is equal to 681 degree Celsius. Now we will move for the next, that is the temperature at the end of constant volume heating. So process 5 to 1 is the constant volume heating process. So for this heating process, what is the relation in between this pressure and temperature? So if we observe, P5 by T5 is equal to P1 by T1. So we can write T1 is equal to P1 by P5 into T5. But in the given data, it is given P1 is equal to 2P5. So we can develop here P1 by P5 is equal to 2. And T5 is known, that we have calculated earlier. So one thing is that we have to take values only in Kelvin. So here T1 is equal to 954 into 2, that is 1908 Kelvin, which is equal to 1635 degree Celsius. Now we will move for the next question, that is temperature at the end of constant pressure heating, that is T2. So constant pressure heating is process 1 to 2. So T2 we have to find out. So again we have relation V1 by T1 is equal to V2 by T2. So T2 is equal to T1 into V2 by V1. So V2 by V1, that is nothing but the cutoff ratio. So cutoff ratio is given 2, and T1 is also known, that we have calculated in earlier, and we have to take this value in Kelvin. So if we take this Kelvin, we will get the answer 3816 Kelvin, and in degree Celsius 3543 degree Celsius. Now we will calculate temperature at the end of isentropic expansion. So isentropic expansion is the process 2 to 3. So we will calculate here T3. So T3 by T2 is equal to V2 by V3 raised to gamma minus 1. Now if we observe for this V2 and V3, we will multiply and divide with V1. So it will become V2 by V1 into V1 by V3. Now V2 by V1, that is the cutoff ratio, that is known 2. Now V1 by V3, so V1 and V3, this ratio is not known, but we can plot here V1 is equal to V5 and V3 is equal to V4. So V1 by V3 is equal to V5 by V4, and this ratio is given in the question, so which is equal to 1 by 15. So 2 into 1 by 15 bracket raised to 1.4 minus 1, so which is equal to 0.447. Now T3 is equal to, so T3 is equal to T2 into this 0.447. So 3816 into 0.447, which is equal to 1706 Kelvin, which is equal to 1433 degree Celsius. Then we will find out what is the efficiency neta. Neta is equal to 1 minus T3 in the bracket T3 minus T4 divided by gamma T2 minus T1 plus T1 minus T5. So all these temperatures are known. Gamma is equal to 1.4. We will put all the values, and when we calculate we will get the answer 0.6185. And how to convert it into percentage, that is we have to multiply this answer with 100, that is 61.85%.